Okay, so thank you everyone for being here. Thank you very much for the organizers. And yeah, so today what I'm gonna do in this presentation is change a little bit the topic now. So we've been talking a lot about social science and like scientometrics and stuff like that. We're gonna go into chemistry now. So if there's any people that do chemistry here, can you just to know what the general like vibe is? Perfect. Okay, so yeah, we're going to be talking about augmenting large language models with chemistry tools. I asked that question not because I'm just going to be like talking about chemistry, but like just to know if I need to like um, be more specific about some things. So just to be
the others, yeah.
yeah. So to give a bit of background about me, so I come from Colombia. It's this nice little country in the middle of the world, of course. And yeah, so I did my bachelor there in chemistry, and so yeah, it's a really cool place because like, okay, I come from Medellin. There's a lot of mountains there, a lot of animals. I love that. Then I moved to the US for a little bit in the University of Rochester. There I started kind of my path in language models and data science. Then I moved to Germany in the Max Planck Institute for Mathematics and the Sciences. And then I stayed for like half a year there. And now I came to EPFL in Switzerland, where we have mountains again, because both these places were really flat. So I'm really happy. Sometimes they're like too accessible. So I do things like this, which is really fun. So anytime you want to come to Switzerland, it's really fun. Come try it. Now let's actually talk about science. So basically the question we had last year when we did this work was, can we use LLMs, large language models, for chemistry or for like practical chemistry? Like what can they do for us as chemists, right? We've seen a lot of applications today about them being used for social sciences and stuff like that. But like today we just care, or like at least in my presentation, we care about chemistry. So let's say the main problem with LLMs is that whenever you ask them a question about chemistry, they're going to come up with something random that actually makes no sense if you're a chemist. Like they look like they make any sense in the surface level, but when you actually look at the answers, they kind of make no sense. So the short answer to that question would be no, they're kind of like not useful for chemistry. But if we combine them with certain tools, then yes, they become more useful. And this is what I'm going to show today. So like first thing we need for this is tools. And so regarding tools, chemists have a lot of tools. And actually, I'm guessing some of you are from Lee Cronin's lab. So yeah, you develop a lot of tools. But we also develop a lot of tools. So for instance, chemists have tools for design, right? So first thing in design is like, if you're a chemist, you want an objective. You want to know what to make, right? And for this, you want to know, like, you want a specific application. So maybe you're designing materials, you may be designing drugs. So yeah, what to make exactly. Then there's also tools for planning. So how to specifically make whatever you have designed to make, right? So yeah, or like what experiment to do next and so on. To execute, you have robots, you have a lot of tools that help you with this. And then for analysis, this is like traditional. There's also a lot of computational tools that help people analyze whatever experiments they make. And of course, there's a lot of computational chemists doing automation, basically, like of all of these workflows. And so now we have that, like now that we have all these tools, the next thing is going to be an operator. And the operator is going to be a language model. So I don't think I need to introduce them at this point. I think the people in social sciences have done a great job at introducing them. So I'm just going to say, yeah, people were kind of thinking that like language models might, or at least almost achieved artificial general intelligence last year, which by now kind of like faded out, I would say. But yeah, they do have some impressive capabilities, and we can exploit them for some things. So let's say they can reason to some extent, and they can use tools, which is going to be very useful for this. So yeah, you have a lot of providers, OpenAI, Claude, Mistral, and so on. And they, we're in a point now where they all do like a very good job. So ChemCrow, this is the way we gave to this system. It's basically just an LLM using computational or like using chemistry tools. So let's say to our LLM, which in this case was GPT-4, we gave certain tools, and one of them was like molecular, or like one of these sets of tools was molecular tools. And this is basically tools that allow you to calculate molecular properties, such as like molecular weight, or I don't know, descriptions of molecules and so on, name converters. So if you see a molecule like that, that's a graphical representation. You can consider that as a graph, but you might also write that molecule as text, right? You have like UPAC name, which is like the like naming you're learning organic chemistry when you're in college. But you can convert that into smiles, which is another representation, and so on. Like the LLM cannot do that itself, which is kind of disappointing because it's fairly easy with tools, but whatever. And yeah, databases, so that the language model can access properties of molecules and many other things. The second set of tools would be reaction tools. And so for this, we have retrosynthesis. Retrosynthesis is just a way of planning how to make something, like coming up with a recipe, how to make certain molecules. So let's say you have that molecule that you want to make. Well, how do you make it? Like what specific things and in what order do you mix them and what conditions and so on. So this is retrosynthesis. And then the second thing that we're going to have, and it's probably one of the most, let's say, interesting things about this work, is going to be that we connect with a robot as well. So not only do we like make things, let's say, theoretical, but we also give the language model the capacity to actually, do things in a real lab through a robot. There's two other set of tools. So the other one is going to be like general tools, which is a Python interpreter, so that it can make computations in Python. Literature Q&A, so basically just a way of reading papers and like trying to gain more context from the literature, the scientific literature. And finally, search, which is just like Google search. And finally, there's safety, a set of safety tools, which basically are built there so that the system doesn't suggest something like dangerous to users, or that it doesn't itself do stuff that is dangerous, right? So mixing certain chemicals is not advisable because it like produces toxic fumes, right? And you don't want that, or it might explode or stuff like that. So this is just like to make sure that like these things don't happen. And then there was another reason for doing this. The other reason was that like because people thought that like large language models might be like super smart, then they might become conscious, and so we need to protect us against that. That was like kind of fun in social media, but now we know that's not going to happen. So yeah, this is the way it works, right? So we already mentioned the operator, which is the LLM. We mentioned the tools, which are those that I talked about before. And now this is the way that it's actually going to work. So we have this idea of chain of thought reasoning loop, which is basically we give a task to the system, and then the system is going to try to like plan what these next steps are going to be. I'm going to explain that with an example, but basically here, the language model is going to think about like the task that it has. So it's going to like try to plan ahead what it's going to do, and then it will select an action. So this is like one of the tools that it has access to. It's going to use one of the tools, and then it's going to analyze the output from that tool to continue with this. So like once it gains information from the environment, it's going to like think again and continue planning, right? So I'm going to illustrate this with an example. So there you have ChemCrew. And so the task is something as simple as this: plan and execute the synthesis of an insect repellent. Again, this is like without any context. It's just like the system, like, built in LLM with the tools. And so this is the only task that we give it to it. So the LLM is going to take that query and let's say, think about it and produce this text. So it's going to say, I need to know which insect repellent to synthesize. Obviously, if you want to make something, you need to know what to do, right? So it will do a literature research to find a common insect repellent. So again, this is just a language model speaking. And then the next thing it's going to do is select a tool. So in this case, well, it said it's going to select literature search. So that's what it does. And then it tries to search common insect repellent. And then the tool is called in the background. And then the answer is given to the language model. So in this case, these are some options that the language model can like choose from. And so that was like one cycle. Now we go to the next cycle, which is going to be taking that answer and like, analyzing it to continue like the execution of the tasks. So now, yeah, okay, I will choose DEET as the insect repellent to synthesize. Then it needs to get the smiles of DEET. The smiles is this like graphical, like this text representation of the molecule. And so, yeah, it uses another tool that converts DEET into like the smiles. And so it gets the smiles. And then it continues like that. So now that I have the smiles of this molecule, then I will plan the synthesis. So it calls the retrosynthesis tool. The retrosynthesis tool gives it a recipe, and then it will take that recipe and execute the synthesis, right? So it just like calls this tool, which is calling this RoboRxN. This is just like a robotic platform that we have in Zurich for chemistry, like specific for that. And then in like 3 hours later, well, the only feedback that we get from this is that the synthesis procedure was completed. Now, we, of course, actually like went on and analyzed in the lab that did it actually make what it was trying to make. And so, yes, I mean, yeah. So let's say that was a pretty easy example. Like for the chemist here, this is not new chemistry. Like this is just like super simple. But the thing here is that like, this is like kind of, let's say, very general in the sense that like we didn't really instruct it to do any of this. We just asked it one specific thing, and then it like figure out how to do it, what specific things to use, and solve the thing, right? So like this is going from like directly an objective to the solution of it, which has implications in the real world, right? So all the 3 examples of these kind of tasks was here when we asked to synthesize 3 organocatalysts. So in this case, it did a similar process. It tried to find examples in the literature of organocatalysts. It found these 3, and then it found out how to make them and actually, well, synthesize them. So this is a bit more complex chemistry, but again, this is like limitations of the robot. This is because of limitations of the robot that we cannot really continue and making like multi-step synthesis. But yeah, so that's basically how it works. Now, one of the interesting things about this kind of system is not per se in like coming up with this sequence of steps of how to solve something, because they're kind of trivial, right? Like making a hard-coded pipeline of how to do that specific task is fairly easy, because yeah, you have to like find what you need to do, then plan how to do it, and then send it to a robot, right? That's not like that hard. The interesting thing comes whenever you have like unexpected behaviors, right? So for instance, in this case, and like on the synthetic cases that I just showed, you have examples like this, like, you know, Chemcro just sends some instructions to the robot, something like this, and then the robot will say, error, the vial has less than 15 milliliters of liquid that for like, which, you know, for some reason it needs to use. So that's like one limitation of the hardware. So if you have a hard-coded pipeline, this will just like, you know, it stops there because this is an error that you not always account for. But like if you have an LLM, it's as simple as, okay, I'm just going to add some solvent, and it automatically corrects the error and continues with the workflow. So the point here is adaptability. If you can kind of like rely on the LLM to do this kind of error correction, then the workflows are going to go rather fast. So this is nice. So yeah, let's say this is just a demonstration of how you can automate certain processes in science, and especially in physical sciences where you actually need to go and do experiments in the lab. I'm going to show you other examples of this, but basically one of the big struggles with developing this kind of system is evaluation. So let's say this is very hard to evaluate for, let's say, mainly 3 reasons. One of them is that the objective is not always well defined. So as you saw, the input that we give to the system is just very arbitrary. I asked it to synthesize certain thing that is very abstract, but it could have done something entirely different. That's also correct, but in a different way, right? So that's, you know, kind of hard. Many solutions are possible. So again, same thing, you know, you ask it for something, it solves in a different way, might be okay, but like the ground truth is not the same. And then there's a lack of baselines, right? So this kind of automation system is very new. And so you cannot really compare with anything else because you don't have that, right? So what did we do? We just designed 14 tasks to test the capabilities of this system. like we just manually decided like what we wanted the system to do, and so we're going to evaluate them on that specific, on like those 14 specific tasks. GPT-4 was used as a baseline with no tools, so we just like they basically ask ChatGPT, hey, can you do this for me? And if it does it, cool. If it doesn't, okay, then it sucks. And we ask the same question to CamPro to see if it can solve it better. And finally, for evaluation, well, we just took human evaluators, which is the most expensive way of evaluation that we could come up with, but also the only one we couldn't rely on. So yeah, let's say we did that. And here are some of the results. Just to understand this plot, basically what we did here is the following. So here you have all the 14 tasks on the left. And then the x-axis is going to be the delta mean expert scores, which is just like how, like what is the mean difference between the scores between CamPro and GPT-4, right? So like CamPro, which is the one we designed, and GPT-4, which is just the like baseline in this case. So a purple bar in the like right direction means CamPro is better. Pink bar to the left means, well, GPT-4 was better. And finally, like the tasks are ordered by difficulty here on the y-axis. So yeah, the general pattern you can see here, I think, yeah. So the general pattern here is that like as tasks become more difficult, then you have kind of like this shift towards the right, meaning like CamPro handles better harder situations or harder tasks, right? GPT-4, as I said, just like sometimes work better, but it comes up with like random things or just like, makes things up that not necessarily make sense, right? So in the harder cases, CamPro does better. Now, on that side, I'm just like gonna be a bit more specific on what the tasks were. So that's just a subset of the tasks, which is like actually tasks that involve synthesis. And so here you have a bunch of molecules. Each of them increases in complexity, so like they're harder to make. And so, yeah, what you see there is basically, I mean, the same thing. So like purple bar high means CamPro is better, GPT-4, or like pink bar higher means GPT-4 is good, right? So in this case, what you see is that like what I try to illustrate here with this little like dotted line here is that like that's kind of the pattern there. As you get like more complex tasks, CamPro kind of just like keeps a similar level of performance, while GPT-4, it does actually better in simpler tasks. But whenever it becomes very complex, the performance just like goes very low. And the reason for this is that like for very popular molecules, if you ask GPT to tell you how to make it, well, it will just like spit out an answer that it learned by memory, because these are like molecules that are everywhere. But if you go more complex, then it will not make sense. While CamPro is relying on some software that we already know works well, and we can, test and rely on. So yeah, well, this was already like a few months published in Nature Machine Intelligence, so we're finally done with that. Here's a team, so like special thanks to all of them. And so I'm not gonna conclude yet. This is just like, let's say the whole point of this work is that CamPro can autonomously like solve generic tasks in chemistry. So this is like pretty much whatever you can ask it, it will try to give you an answer. If it doesn't have enough tools for that, it will just tell you, I cannot solve it, which is quite different from what you would expect from ChatGPT or whatever else that will tell you, oh yes, definitely. Here you have the exact answer that makes no sense, but it will tell you something, right? And so CamPro is flexible. It can adapt to unexpected outcomes, which is one good thing as compared to like hard-coded things. And of course, better evaluation is needed. We've been struggling with that for a while. And finally, CamPro is modular. So like if you add new tools to expand use cases, well, you will get a better system eventually. Now, I still have some time, so I'm just going to talk about what's next. Let's say first thing is better understanding of literature, right? I'll talk about that a little bit more. And then a specific use case. So like in more research relevant tasks, right? So here, let's say the problem is that like we just try to do everything, right? Like how useful is a language model in chemistry? And chemistry is a huge field, but we were like, yeah, whatever, all of chemistry. It might be more interesting if we just like focus on one specific like subfield of chemistry, and we decide that like, okay, we do that. We try to actually discover something or like guide some sort of research with these systems, and then we see if it actually helps us. So let's say for understanding of literature, the problem here is that in chemistry, let's say we have sort of a data crisis. We don't have a lot of data in a like machine readable format, right? So most of data is actually in papers. So what about we rely on LLMs for reading papers and trying to put them in like a machine readable format, right? So yeah, a lot of examples. But what I want to show you here is that there's challenges with this. You cannot just ask or like give a paper to a language model, at least a paper in chemistry to a language model, and ask it to like make it digestive for you, because you have things like this. So for instance, here in the right, you have like in the paper, they're talking about C10 of diketone 28. What does that mean? I don't know, unless you go to that figure and then you look at the molecule and then you understand what exactly they are referring to. If you do that, then you might understand a little bit better, right? However, the language model, now they do, but like at least, you know, only like from this year on, they didn't really have access to like reading images. They didn't know how to interpret them. And even now they kind of like suck at that. So even if you give images and like the whole text to the language model, they might still not understand or like be able to synthesize what's going on here with diketone 28, right? So what do we want to do? We want to, well, like try to develop tools that can better like understand literature and put it in machine readable formats, or at least formats that like are more readable for language models. This is a challenge in itself, and so we have done some work on that. This is like the main pipeline. This is actually very similar to one of the works that were presented in the previous session. It's basically just RAG, like retrieval augmented generation. You give like context to a language model. You like ask them to give you certain things in specific ways, and yeah, this way you can actually extract synthesis, for instance, from synthesis papers, which is very useful. There's already this is already published in a conference, and yeah, but I forgot to put the link. Sorry. So there are some preliminary results that for some reasons we can't see there. But as you see, let's say the best performance we get ever is like 0.79 in an internal benchmark, which is not really good. You would like very high accuracy with these things, especially because like you're not trying to predict anything. You're just like translating things, right? So you want high accuracy. And yeah, so like these are all the people involved in that work. And then finally, let's say in my last minute, I'm just going to talk about like research relevant use case. So in the last year, we focused more on inorganic materials. Now we're going to take a switch from organic to inorganic. The reason why we're going into inorganic materials is that more reasoning is done over text in this field than it is on organic chemistry. So in organic chemistry, you're like, I mean, as I showed before in that image, you're relying on like molecules, which is like something that you usually represent graphically. While in inorganic materials, you might talk about like things more, right? Like more reasoning is done in text. All the synthesis you report as text, and so this might be more suitable for language models. So yeah, this is where we enter this other project, and we specifically are going to focus on single atom catalyst. On the synthesis of single atom catalysts. And so, yeah, well, I mean, this is very preliminary work, but basically like the point is having a system that you ask it, hey, how do I make this specific catalyst that I want to make, or a catalyst that has certain properties, or a catalyst that can like catalyze certain type of reaction, right? And so the language model here, or like the system, would have to figure out what metal and atom, or like atom to use, what type of support to use, what combination of them, and then like how to control the properties, what specific procedure to follow, and so on. Yeah, I think I'm gonna just like skip this. This is just like a very, very basic and preliminary thing, how it's working. And yeah, this is all the people involved. All of us are from NCCR Catalysis, which is this kind of like big collaboration inside of Switzerland. So this is like a 3-group collaboration inside of Switzerland. It's very exciting because like we're gonna have eventually experimental validation of these things in a research relevant use case. So with that, I'm just gonna say some special thanks to all my group in EPFL, to all the people in CCR, and finally, thank you all for being here. And yeah, I'm open to any questions if you have any.
Thank you for the talk. Thank you for the talk.
You're welcome.
Are there any are there any questions from the audience? Well, there's one all the way at the other end of the room. And okay, another one there.
Thank you. That was a really interesting talk. I don't know if I missed it, but I wondered if you have any tools developed or are relying purely on the language model itself for unknown molecules. Let's say if the example you showed of the, what was it, like a DET was a known molecule, right? You asked for a anti something and it found it, or okay.
Yeah, that's a great question. So I mentioned like way before that there's like tools for design of molecules. So let's say here, once you give it a function you want, so in this case, we want an insect repellent, you can do two things. First thing you can do is just look up in Wikipedia what are insect repellents and get something from there. So that's what happened. Like DEET is actually something that, like, you know, this is actually one of the most used insect repellents ever. So it's just like look up in Wikipedia, get like the actual thing that will solve your task, and then learn, like, try to find how to make it. But like, given that we already have certain tools that, like, to some extent work to like design you a molecule with certain functional, like certain properties, then, you know, we might easily just replace that with like a new molecule. So let's say, hey, I want a molecule that can be used as an insect repellent, but that is also novel, right? And so it will try to, let's say, you know, do something in that direction. We actually have an example like that, which I just didn't show it here, but like for time, but yeah, similar way. What it would do in that case would be like trying to find in the literature what molecules are used for that function, and then trying to analyze them and make modifications, like, or like plausible modifications to them, so that it's novel, but it's still kind of like similar enough to whatever exists to like target that function.
And that step of finding a new molecule, is it language based or is it an algorithmic kind of?
There's an algorithmic way of doing that. Yeah. I mean, here, like, basically the language is just an interface between the let's say the user and the tools, just like a, let's say, structured interface, right? So like you as a user just tell it what to do, and then it will figure out what to do. But like everything is based on the tools, right? So the language just like the language model just selects what tools and like in what order, right? And yeah, but the generation in itself of the molecules would be based on whatever tool that you have. Yeah. Thank you for the question.
Thank you for the talk. So my question is, how scalable do you think this approach is of just adding more and more tools? So do you imagine you will have versions of ChemPro that are tailored to material design, some to organic synthesis, some to biochemistry, or can you really have one for everything?
That's a good question. I mean, I could tell you what's like more practical or what would be more desirable, right? I don't know if like one for everything will be the best solution or would work at all, right? You know, it just might. But like I'm inclined to think that no. I mean, it would be better to design like specific systems for like, let's say, one field. Still not like narrow enough so that it stops being like generally useful for that field, but yeah, let's say in this case we kind of focus too much on organic, but like still we made it very wide, right? So let's say what's coming next, or like what should come next, yeah, should definitely include more targeted, like, let's say, tools, but also like, yeah, yeah, objectives in general. So this is why we're kind of like targeting inorganic synthesis of inorganic materials now, because it's like more specific. And so we might like just, design the specific tools for that. Because one of the things that we found during this is that we actually don't have enough tools. Like there's a lot of tools that we realize, or like we find out that we don't have yet, that might be useful for these things, but also for us as humans, right? So we have to develop them as well.
A fascinating talk. So I'm interested in the heterogeneous catalysis setting.
Mm-hmm.
So in that sense, it's where chemistry meets material science too. So the one thread that I guess I drew from, you said limitations, was the LLM's inability or limited ability to identify these graphs and in some sense discern that structure. But from my standpoint, these are morphological questions, so more in the direction of computational geometry. So this is maybe my question. Computational geometry tools are being developed or have been developed in material science context, especially the heterogeneous catalysis.
Mm-hmm.
So where might tools like computational geometry interface into this catalysis setting in the search for new catalysts?
Oh, wow. I've seen work doing that, but like especially for analysis. I mean, but that's a great question, by the way. I'm also not an expert in that, but I've seen work on that. Like basically tries to like, so like whatever, you make a material and then you like do microscopy on it or like whatever other type of analysis, and then the computational tools are like trying to like understand what is in that image, right? At least this is kind of what I'm getting from that. And yes, I've seen tools that do that. They work very well, but again, yeah, that's like something more specific, right? So like this, I would think it would work if you have like a ChemCro for inorganic chemistry, but like for organic, I wouldn't see it as useful. And so like, I'm just coming back to his question. That's where you actually need to kind of like start narrowing down. And for that specific question,
not you. I'm just.
Yeah, I would just like, if it works, if it's useful for chemists, I would think it would be useful for this. I'm just not like an expert in that, and I wouldn't know exactly how to use that in like this, in this field. That's a great proposal.
So maybe the last question for today.
Andrés, great talk. So I'm curious, is your tool fine-tuned at all? Is it kind of LLM agnostic? Could it be attached to any underlying LLM? So next month, Claude's better, you attach ChemCro to that. I'm just kind of curious why ChatGPT-4 outperformed your system when it's a system built on an LLM.
Yeah, so like it is LLM agnostic in the sense that you can, in principle, plug in any language model. I'm just coming back to the results slide. So like it is agnostic in the sense that you can just plug in anything. Now, so this was here like a year ago, almost, a bit more than a year now. And the thing with this is that like back then, the only model that like worked like very good was GPT-4. Now you have Claude and like Mistral and whatever, all of them work pretty good. But back then, this was the only one that like that actually worked well. And working well in this case is like actually following the format that we wanted to follow, right? Like it has to follow this loop of like making, a thought and then selecting a tool and all of this. GPT 3.5, which is like the normal like ChatGPT back then, couldn't even do that, right? So that's why GPT-4. And the reason why it sometimes outperforms is because, like, for instance, here, this is just like synthesize certain molecule. And so here you have molecules like atorvastatin, which is like super big, well, not big, it's still a small molecule, but this is like a drug-like molecule, which is kind of like large and more complex molecule. And here you have paracetamol, which is like a super easy molecule, right? So for this, you have a lot of examples in the literature how to make it, or like in the web how to make it. So GPT-4 just like probably memorized one of those. And so whatever answer it's giving, it's perfect because it's like literally spitting out something that someone already made. Now, ChemCro will just use the tool, which is not necessarily like as detailed, but still okay. Now, in this case of atorvastatin, ChemCro does well because like it's using the retrosynthesis tool that is in the background that works okay. while GPT-4 is just trying to come up with how to make that molecule that it doesn't even know the structure of. So that explains like the results, and yeah, we could go a little bit more in detail into the other cases, but it's something similar. In the end, it's like the easy cases, GPT-4 kind of knows them by memory, but whenever he actually has to think a little bit more, then it doesn't work. Yeah.
Thank you. In the interest of time, if you have any more questions, please find Andrés or email him afterwards, and let's thank him one more time.